Good morning. Let's start a new chapter today. If you can count, it's already chapter 4, so time really flies, right? Chapter 4 is all about periodicity and symmetry. So we'll be seeing how periodicity and symmetry affect the properties of the solutions to Maxwell's equations. So this will be quite an interesting chapter if you're interested in being efficient or lazy, in the sense that it will show an easier way to gain information about the solutions to Maxwell's equations without actually solving Maxwell's equations. So that's quite an interesting approach, I would say. So this is what we have on our plate for this chapter. Before we start, I would like to revisit the Helmholtz equation. You obviously remember that we derived the Helmholtz equation in the very first class. But there we said that the formulation we derived there was only valid for media where the refractive index was piecewise constant. So here in this chapter we need to generalize this a little bit so that it's also valid in non-uniform media. Media where the refractive index epsilon can vary as a function of the spatial coordinate r. So let's see how we do that. So of course Maxwell's equations involve the rotor of the electric field being proportional to the magnetic field, minus j omega mu, and mu in general case is a function of r, h of r, and then of course we have a related equation, a dual equation if you want, involving the curl of the magnetic field, j omega epsilon r, and this time epsilon can be a function of the spatial coordinates as opposed to just a constant. So now what we would like to do is to combine these two equations in one equation, just as we did for the Helmholtz equation. That's of course not rocket science, because we can derive from the second equation that the electric field as a function of the spatial coordinate is 1 over j omega epsilon of r curl of the magnetic field, like this. And then we can just substitute that in the first equation, and then we simply get the curl of the electric field, which we calculated to be 1 over j omega epsilon of r, curl of the magnetic field, equal to, what is our right hand side, minus j omega mu of r, h of r. Okay, we will be looking at situations where epsilon is in general a function of the spatial coordinates. But what's a bit rarer in practice is that mu varies as a function of the spatial coordinates. So mu will just put mu as a constant and a non-magnetic media. So we're only going to look at that case. That's the most important case in practice. So if we slightly rewrite this a little bit, bring stuff over to the right-hand side, we actually get the following curl, 1 over epsilon curl, magnetic field, and then j multiplied with minus j, okay, so that just disappears, and then finally we have omega squared mu h of r. And this is like the Helmholtz equation, if you want, for situations where epsilon varies as a function of r. And since epsilon varies as a function of r, we cannot bring this epsilon outside of the curl. That's forbidden because there's this differential operator in front of it that does not work. So we cannot bring the epsilon to the right-hand side, just like we did in the beginning of this course. Okay, this is a very important equation. We will be working a lot with this equation. And actually the way we're going to look at this equation is we're going to consider omega as the unknown in this chapter. That seems a bit odd, but the viewpoint we'll be taking is we have a certain given structure, given by its epsilon profile here, and we're going to ask ourselves the question, if we have such a structure, like a waveguide, for example, or a cavity, what frequencies do the modes to the allowed solutions to Maxwell's equations have in this problem, in this case? So that's the problem we're looking for. We're looking for the frequencies of the solutions, of the modes of a cavity or of a waveguide or something like that. And to make this equation a little bit more compact, we will be introducing an operator capital theta, which will be defined as follows. So curl 1 over epsilon r curl. And that's an operator. What does this operator do? Well, it first takes the curl of a certain vector field, then it divides by epsilon, and then it takes the curl again. So this is the definition of this operator. This is what this operator does. And then you can more compactly say that this operator capital theta, operating upon our magnetic field, H, let's save some space here, that's equal to omega squared mu of H. So this is just more compact rewriting of that equation up there. Okay. This type of equation, anybody have any idea what family of equation this belongs to? So we have an operator operating upon something, and what is the result? What do we get back? We get back that same something, but multiplied with a constant. That should ring a bell. That's, yeah, I see people nodding at the back. These are? Yeah, these are the eigenvalue problems. You typically know them, I guess, from matrices and vectors and stuff like that. Here we have a bit of a generalization involving operators and functions. So our H is called the eigenfunction. So it's a function, whereas if we operate upon it with a certain operator, theta in this case, we get the same eigenfunction H back, but multiplied with omega squared mu, which is then the eigenvalue. So we will be talking a lot about eigenvalue problems and operators in this chapter. So this chapter will also be very much more physically inspired. Physicists like to work a lot with operators and stuff like that. So this is something we'll be doing in this chapter. So okay, we have an eigenvalue problem with an eigenvalue omega squared mu. It would be really nice if we could sort of mathematically prove that omega squared mu, but okay, let's say that mu is equal to mu 0, so that omega squared mu 0 is a positive number, because that would result in the fact that omega itself would be a real positive number, right? Mathematically, it's not excluded that we have an eigenvalue problem where the eigenvalues are negative, and then we would have that omega squared would be negative, so omega would be imaginary, and that would not sit well for physical reasons, right? So we would like to prove somehow that the eigenvalue of this particular theta operator has positive eigenvalues. So in order to do that, we need some extra concepts, and the first concept we need for that is the concept of a Hermitian operator. What is a Hermitian operator? So let's make some space here. The important context of hermiticity. What are Hermitian operators? Well, in order to discuss this, we first need a definition of a scalar product. Remember also from previous chapters, scalar products, you can define them in many ways. You have a bit of a degree of freedom to fix that. And in this particular chapter, we'll be looking at the scalar product between two functions, f and g. And we're going to define this as a volume integral of f, complex conjugate, so here we will be using a complex conjugate, scalar product G, like this. So this is the definition of a scalar product. And again, you could come up with different definitions, for example, without the star or with a weighting function in front. I mentioned before, this is the degree of freedom we have. In this chapter, we'll make this choice for scalar products, and as long as we live with the consequences, that's fine. So that's just a definition. One of the consequences of this definition of scalar product is that if we look at the scalar product between f and g and we compare it to what happens between g and f, you will see that they're related by complex conjugate. So that's the relationship. It's not a commutative operation. If you exchange the orders, the price you pay is a complex conjugate. And it also follows from that definition that if you take the scalar product of a function by itself, with itself, then you get something which is real valued. And this is something the physicists like, because then they can associate the definition of energy to it, so that there's energy which is positive. Okay, now that we have a definition of a scalar product, we can define what it means for an operator to be Hermitian. So if we have a certain operator, and we'll use for that the Greek capital Xi or something. My Greek is a bit rusty, but I think this is the capital Xi. Or not, perhaps somebody knows Greek better than I do, no protests. Anyhow, this operator with this particular symbol is Hermitian if and only if it doesn't really matter in evaluating the scalar product whether you operate first on the second part or whether you have the operator operating on the first factor in that product. This is a definition of an operator which is Hermitian. You can either put it in the second term or in the first factor. It doesn't really matter, you get the same result. This is a definition of a Hermitian operator. Now, some of you might have heard the term Hermitian before, right? In the context of linear algebra. I guess you all know what a Hermitian matrix is. Some people nodding, some people give me blank stares. But anyway, a Hermitian matrix is a matrix which is the same as its Hermitian conjugate, which is transpose complex conjugate. And you might wonder whether there's a connection between the concept of a Hermitian operator and a Hermitian matrix. And of course, there is a link, there is a relationship. You can easily prove for yourself at home, as a nice exercise, that if you take this very general framework here of operators and scalar product, and you apply it, for example, to the case where as operator, say you have an operator which is defined as taking a matrix product, and as a function, rather than having a function f, we'll have objects which are column vectors. And if finally, for the definition of scalar product between two functions, but the functions will be then column vectors, if you define the scalar product between these two objects as follows, so the scalar product of the Hermitian conjugate of the x vector with the y vector, if you make all of these equivalences, then you can prove for yourself that the concept of having this operator being Hermitian, that's equivalent to the fact that this matrix will be Hermitian. So this is the way these two concepts match, really, what's the relationship between these two concepts is. But talking about operators is something more general than talking about linear algebra stuff. And there is, of course, a relationship between the two of them. We've encountered many times in the chapter on numerical methods that we started out from a general function, a problem involving these functions, and then, due to some numerical technique, we were able to transform that from a differential equation, for example, with operators, to a linear algebra problem, which could be solved on a computer. So this is not really new. Okay. Now we know what it means for a function to be Hermitian. The question we can ask ourselves, our newly found friend, the theta operator here, is this operator Hermitian? That would be interesting to prove. If we want to prove that, we have to look at a situation where we have first the operator operating upon, for example, the second part. And then gradually we want to move that operator to an operator operating on the first factor here. So in order to do that, we'll need to peel away the different layers of the operator. Remember, the operator consists of curl 1 over epsilon curl. So we would like to have some sort of theorem that helps us to move a curl from a second factor in a scalar product to a first factor in a scalar product. This is, of course, something that we will be needing. And for that, let's open some small parentheses here and try and derive such an equation that could be helpful. We go back to our favorite book involving lots of formulas involving vector analysis. And there is a formula which gives you the divergence of a vectorial product. And that turns out to be equal to the following expression. So we have a curl operating upon A, and then we have a second term where there's a curl operating upon B. And here we can already see that this goes in the direction of what we want, because we want to move a curl from operating upon A to a curl operating upon B. Of course, in our scalar product, we have a volume integral. So let's take a volume integral of this thing. Let's also bring this here to the left-hand side. And then we have a volume integral of A curl B dv. So that's the first term. If we then look at the term involving a B, then we have B curl A dv. And then finally, if we bring this thing also to the right-hand side, we have then minus a volume integral of the divergence of A vector B. Right. Okay. At this point, we can do a little dance for joy because we know what this thing is, right? We have evaluated this many times before in the past. If you have a volume integral of a certain vector function, of the divergence of a vector function, we know we can simplify this to being a surface integral, so over the boundary of V over the stuff of which you took the divergence, which is in this case the vectorial product A vector B. So finally, if we bring everything together and make it a bit more cosmetically pleasing, we have a volume integral of A curl B dV, and we can transform this into a volume integral, and then let's just exchange the order, of curl A with B. So remember what we've done here is we've have the curl operating upon B, and now we have it operating upon A. We can exchange that, and there's a small price to pay, and this price is a surface integral, the surface integral of A vector B ds. So this is the little equation that we will be using to prove that our operator theta is Hermitian. And now we can start on that proof. So we have two functions, we have f and g, and we have the operator theta operating upon g, and we want to figure out that this is equivalent to the operator operating upon f, and only then taking the scalar product with g. So let's see what this means. By definition, this is a volume integral of f complex conjugate, right? And then we take the definition of theta, that's an operator consisting of curl 1 over epsilon curl G dV. Okay. Just to make our life a little bit easier and easier to interpret, what we're going to do is just to add some simple parentheses. So this curl here, this first curl, operates upon everything which is in parentheses here. And now that we write it as follows, we can identify this equation with the auxiliary equation we have before here. So we can say that our A is f prime, and our B is everything which is in between these parentheses here. So now that we know that, we can apply that formula. That formula tells us that we can bring the curl over to our A factor. So we can have the curl of f prime. Remember, the curl is just a symbolic vector involving partial derivatives. There's no complex number involved, so the complex conjugate doesn't really affect it. And then we have our B, which is 1 over epsilon curl of G dV. And then there's a price involving a surface integral. I'm not going to copy it here, but this is a surface integral. What are we going to do with this surface integral? Well, we're going to just say, let's put this surface integral to 0. Let's neglect it. Can we do that simply? Well, we can say, okay, there's two reasons why this is valid. We will restrict ourselves to two situations. One is a situation where the volume that we're considering is, of course, a volume at infinity. And at infinity, we'll say, okay, the fields have decayed. There's no more field left at infinity. So this is a good reason why then the surface integral at infinity would be 0. Or a different situation we will be considering is a situation where at infinity the fields are periodic, positively, negatively, and then keep on alternating. If we have such a periodic function oscillating between plus and minus a certain value, then also because these parts will be cancelling, we can also say that in such a case with the periodic function, this integral will also be 0. So if we restrict ourselves to these two cases, either fields vanishing at infinity or fields periodic at infinity such that they cancel, then we can just simply neglect that second term because it will be identically equal to 0. So the price we pay turns out to be not such a big price after all. Okay, so we started peeling away at the different layers of our operator here and trying to reassemble them in the first vector. Let's now continue that process, and we need to bring then this 1 over epsilon into this thing here. But here it's a little bit more involved. Well, not really involved. You need to be aware of the fact that now this 1 over epsilon here needs to be inside of that complex conjugate. And of course, that's a step we can only take if our epsilon here is real valued. So if we restrict ourselves to cases where epsilon is real, what does that mean in terms of materials you're working with? What does a real valued epsilon mean? Just go back to the course on optical materials. Epsilon real means no losses, yeah. So the imaginary part of epsilon has everything to do with absorption, and we're not going to look at absorption in this case, so nicely well-behaved lossless metals or lossless dielectrics. Okay, let's continue. Then we still have the final layer of the onion here, like this. Okay. Now we can keep on repeating that same procedure we had earlier, but this time we will call this our A, and this will be our B. And then we can again peel away the final layer of the onion and bring the curl to the left-hand side such that it operates upon our A, which now looks like this. And again, since the curl is a real valued operator, there's no complex number inside there, we can write it like this. dV, okay. But what do we have here? We have here nothing more, nothing less than the capital theta operator operating upon F, complex conjugate G dV, which is simply by definition the scalar product of theta F G. So indeed we see that we can bring the theta operator from operating upon G to operating upon F, and we get exactly the same results. So this is the proof that our function, that our operator theta rather, is a Hermitian operator. Why do we care so much about Hermitian operators? Well, later on we'll see lots of properties of these operators, and one of these properties will allow us to prove, which is what I hinted at here, that we would like to have that our omega is a real valued number just for physical reasons. Good. I've talked for long enough. I think it's now time that you guys got your hands dirty with these concepts. What are we going to do? Well, here I've derived an equation involving the magnetic field, H. There's of course nothing that forbids you to start from Maxwell's equations here, and rather than substituting out E, you can substitute H, such that you get another equation involving, this time not the magnetic field, but the electric field. So my question to you is, can you come up with an operator equation for an eigenvalue problem involving the electric fields? It's the first part of the question. And the second part of the question, the operator that you find then, is that a Hermitian operator or not? So that's the question before you do something similar, but with the electric fields instead of the magnetic fields. Good luck. Let's give you some space. Okay. So first step, deriving the operator. So simply starting from Maxwell's equations, calculating then H explicitly from this equation and substituting into that equation gives us an equation that only involves the electric field. Okay. This seems to suggest that this is our operator, right? So the operator in this case is girl, girl. Anybody, any objections? Everybody happy with that? So is this our eigenvalue problem? With our operator being the girl, girl? Who votes for yes? Who votes for no? There's a tentative majority for no. Why do people say no? There was a whole horde of people at the back saying no. Yeah, why no?
Because the right-hand side of the equation we still have a constant that is dependent on R.
Yeah, exactly. So this is not an eigenvalue problem in the sense that we have a certain operator theta operating upon a certain function A, giving you back that same function A, but with a certain eigenvalue. The eigenvalue here should of course not depend on the spatial coordinate R, otherwise we don't have an eigenvalue problem. So this is not an eigenvalue problem. What this is, rather, is something which is called a generalized eigenvalue problem, because you could say that this equation takes the form where we have a certain operator operating upon a function A, giving you back that same function A multiplied with a certain eigenvalue, but rather we also have another operator, and I'm running out of Greek symbols here, let's call it gamma, another operator gamma operating upon the right hand side. So this is a regular eigenvalue problem. This is a generalized eigenvalue problem where there's still an operator operating upon the right hand side. So generalized eigenvalue problems, they also exist. You also have them in, for example, linear algebra. In linear algebra, there are also numerical routines which solve a problem of the following form, where we have a vector, a matrix operating upon a vector, giving you that same vector back, but multiplied by a matrix B, and then you have an eigenvalue lambda. So these generalized eigenvalue problems exist. There are numerical routines for that. And you might say, why is this so relevant that there are numerical routines specifically for linear algebra problems like this? Because you can easily write this and convert this into a regular eigenvalue problem, simply like this, simply by bringing the b to the left-hand side. Then you have a regular eigenvalue problem. So why would there be special numerical techniques taking care of generalized eigenvalue problems? Anybody have any idea why these things still have their place and you can't simply always rely on transforming it into a regular eigenvalue problem? Mm-hmm. Yeah, that could be a problem, right? If b is singular, then you run into numerical issues, and then it's much better to have this b safely at the right hand side where it can't cause any problems, and have your numerical technique take care of that. So if you really want to transform this generalized eigenvalue problem into a regular eigenvalue problem, we can do the same trick, of course, which could have some numerical issues. And in this case, that will not be the case. If we simply divide everything by epsilon, and we say, okay, epsilon, normal materials, they don't have a zero refractive index, right? So we can simply write now curl 1 over epsilon curl of the electric fields, giving you back the electric fields multiplied with a constant omega squared mu. So this is our regular eigenvalue problem for the electric fields. It has the same eigenvalue as the magnetic field, but the operator here looks a bit different. So rather than having an operator curl 1 over epsilon curl, we have an operator 1 over epsilon curl. So that's the first part of the question. Any questions about the answer? Then it's time to talk about answers to the question, namely the second part. This operator, 1 over epsilon curl, is it a Hermitian operator or not? So now you do exactly the same thing as we did for the magnetic fields. You try and peel away the layers of the onion of that operator and reconstitute the onion on the first part of the product and see whether that works or not. So that's the approach you have to take for the second part. Okay, so in order to prove that this new operator is Hermitian or not, we need to look at the following scalar product, of course. So first we have the operator operating upon the right-hand side. And I'm not going to work with volume integrals here. I'm just going to use the shortcut notation of scalar product. That's exactly the same thing. So 1 over epsilon curl, this time operating upon G. So let's try and peel away the layers of the onion. Again, it's very similar to what we did last time. So the first layer is this 1 over epsilon. Remember that there's an implicit complex conjugate here in this scalar product. So here we make use of the fact that we're going to restrict ourselves to situations where epsilon is real, and then we can peel away the first layer. So we have this thing. The second layer now involves a curl. We can use the same equation that we derived earlier that can bring the curl from the second factor to the first factor, and there's a price to pay in terms of a surface integral, which I've told you we're not going to pay that price in the situations we're considering. So that brings us to the following situation. Applying that formula once. If we apply that formula twice, and now bringing this curl over to the first factor, we have curl 1 over epsilon f. So this is what we have when we try to reconstruct this operator in the left-hand side. However, I hope that you'll agree with me that this is something completely different from 1 over epsilon curl, which is what we'd like to have if this operator were to be Hermitian. Here the epsilon comes at the beginning of the operator chain as opposed to at the end of the operator chain. And you can easily verify for yourself that this is not the case, that these are not equivalent, especially when epsilon is a function of r. This is only the case when epsilon is a constant. So for general epsilons, this is not the case. So this operator that we derived for the electric field is not a Hermitian operator. And this also explains why we started working with the magnetic field in the beginning. One reason is that the operator involving the magnetic field turns out to be a Hermitian operator. And in a moment, we'll be seeing that these have lots of interesting consequences. They also are numerically more stable Hermitian operators than non-Hermitian operators. So that's good news, working with the electric field, the magnetic field rather. A second advantage of working with the magnetic field in numerical techniques has to do with the fact that if you have a situation without any current source or stuff like that, that all the components of the magnetic field, they are continuous at the interfaces, provided mu is equal to 1, of course. So then you work with continuous functions, which is numerically easier. And you have a Hermitian operator, which is also numerically easier. So this is why the H field has a lot going for it compared to the electric field, which is perhaps more common. Any questions about all of these proofs and the definition of a Hermitian operator, stuff like that? Okay, I've teased you quite some time now with all of the nice properties that these Hermitian operators have. So it's high time I made good on that promise and started showing you one of these, or these properties of these Hermitian operators. And the first general property of Hermitian operators has to do with the fact that they have real eigenvalues. So nothing related to complex values. Can we prove that? Yes, we can prove that, of course. We start from our eigenvalue equation, which remember had the following form. And what we're now going to do is we're going to take that expression and multiply it on the left-hand side, scalar product with h. So that gives us h, theta h, omega squared mu, h with h. Following step, we're going to take that expression and take the complex conjugate of that expression. So that gives us h, theta h complex conjugate. omega squared mu, complex conjugate, H with H, complex conjugate. Here it's tempting but wrong to say, I know that omega is a real valued frequency because of physical reasons, so therefore this thing is real valued. That's precisely what we want to prove here, because remember, in general, this stands for an eigenvalue lambda, which could be anything. So we can't rely on the fact that in our case, lambda physically means a frequency, so therefore it's real. This is precisely what we're trying to prove for a general eigenvalue problem, Hermitian one, which does not have a priori a certain physical link. So this thing should stay there for the time being. We can get rid of this complex conjugate, right? Because of the definition of complex conjugate involving this scalar product. So with our definition of scalar product, we've seen that a couple of minutes ago, this is real valued. Also a consequence of the fact that we have a certain definition of scalar products, it means that we can use this commutative rules here, and then we can sacrifice a complex conjugate by exchanging the order, the sequence of this scalar product. So we have omega squared mu complex conjugate H, H. There's still a card up our sleeve which we haven't played yet, and that's the fact that our operator theta is Hermitian. That's of course a very crucial part of our story. Since this operator is Hermitian, we can bring it to the second factor in our product. And then we have omega mu complex conjugate H, H. So let's take stock here. We started out from an expression like this, and we've also shown that the following expression holds. And now it doesn't take rocket science to figure out that the conclusion from that is that omega mu is equal to omega mu complex conjugate, right? Because that's the only thing that's different in these two equations, which have the same left-hand side. So therefore we have proven that our eigenvalue is real for the Hermitian operator. So for example, this is something I could ask at the exam. I'm not going to ask you to reproduce this type of proof, but I could ask you, like, explain each of the different steps of that proof so that I can easily understand whether you really know what it is for an operator to be Hermitian, the definition of scalar product, consequences of that. So these are the types of questions that I could be asking at the exam, in case you were wondering. By the way, I also have tentative dates for the exams. I assume you have also seen them in your calendar. If not, they will pop up rather soon. I think it's the second week, Monday, Tuesday, Wednesday, the second week after the Christmas holidays. Okay, but let's go back from the exam to a second thing I want to prove. Because remember, for our particular case, we not only would like to have the fact that our eigenvalue is real, we would also like it to be positive, because we have omega squared mu. If this is not only real but also positive, then from that it would follow that omega is also real valued. This is also something we would like to prove. Now in general, and keep this in mind, in general it's not the case that Hermitian operators have real and positive eigenvalues. They only have real eigenvalues. However, for our particular case, for our particular operator theta, you can actually prove that the eigenvalues are also positive. But bear in mind, this is not a general property of these Hermitian operators. So how do we do that? Well, we make use of something that we've used as an intermediate step when we were discussing the hermiticity of our operator here. Remember, while we were doing that proof, at some point we had the situation that the volume integral of the curl of f complex conjugate 1 over epsilon curl of g, that was equal to our left-hand side here. This was the first step when we've peeled away the first layer of the onion, namely that first curl. So this is an intermediate step that you will find back a couple of pages earlier. If we now say, okay, I will pick my f equal to my g, namely to my magnetic field H, if I make all of these substitutions, then what do I get? I get that h, theta of h, right, is equal to a volume integral of 1 over epsilon. And then I have the curl of h and the curl of h complex conjugate. They of course conspire to give me the curl of h magnitude squared dv. And if I say that my h is a solution to my eigenvalue problem, that of course means that my theta h is equal to omega squared mu of h, right? If I know that, then I know that my left-hand side is also equal to omega squared mu. That's then just a number which we can bring out of our integral. So this is something which is specifically valid for the form of the Hermitian operator that we have. But we do know from the definition of scalar product that this is associated with the energy in the function, so this is a positive number, simply by the definition of scalar products. This is also a rather positive number for the same reasons, of course. And if you now make another restriction, namely that our epsilon is real, not only real but also positive, so we restrict ourselves to the case of lossless dielectrics. Metals are different. They are a special, more complex case, so we'll not consider metals. If we look at what we have here, we have a left-hand side, which is positive. We have a right-hand side, which contains a positive factor. And the only inescapable conclusion is that omega squared mu should also be a positive number. And in that case, we indeed have the situation where omega corresponds to a real valued resonance frequency. And this is what we would like to have for physical reasons for dielectrics. So this is exactly also what we can prove simply purely by mathematics. Okay. And then a final step I would like to take is a step involving orthogonality. They also have a very nice property, these Hermitian operators, in the sense that their eigenfunctions, they are orthogonal to each other. And orthogonal, of course, in the sense, the definition of the scalar product that we used. So let's have a look at orthogonality. And that's, of course, also a very important property if you want to construct numerical methods. We've seen in the past that having orthogonal functions really helps when constructing series expansions, and they also make your methods numerically more stable. So let's suppose we have two different solutions to our eigenvalue problem. We have an H1, which will give you an eigenvalue, omega 1 squared mu, H1. And we have a second solution, which we will call H2, like this. So two different solutions, and we would like to prove that these guys are orthogonal to each other. Now what will we be doing? We will be taking the first equation, and we'll be taking the right scalar product with H2. And we'll also be taking the second equation, and you'll guess it, we'll be taking the left scalar product with H1. So what does this give us? Well, for the first equation, we have theta H1 H2 equal to omega 1 squared mu H1 H2. That's our first equation. For the second equation, we get H1 theta H2. And for the right hand side, omega squared mu H1 H2. And of course the reason why we went for this particular multiplication choice is that we have here these two factors which are equal, which will serve us well in the future, as we'll see in just a moment. Because what we also have is the fact that our operator theta is Hermitian, so we can bring this theta here and have it operate not on H2 but on H1. And then all of a sudden also these left hand sides are the same. So, if this is true, if the left-hand side then is the same, we can simply write that omega 1 squared mu h1 h2 is equal to omega 2 squared mu h1 h2. And now, if we assume for the time being that our two different eigenvalues are different, that omega 1 and omega mu, omega 1 and omega 2, they are different values, then we don't divide by 0, and we can say that h1, h2 is equal to 0. And that indeed means that our function h1 is orthogonal to our function h2 under the definition of the scalar product that we have here. So if our eigenvalues are the same, then we are in a different case. If omega 1 should be equal to omega 2, then that's a rather special pathological case, and that we will call degenerate modes. So what are degenerate modes? Degenerate modes are modes which are different, they have a different field profile, but just by accident, to some fluke of nature, they have the same eigenvalue. And in this case, you can't really say that this scalar product is 0, because of course this reduces to omega 2 squared minus omega 1 squared mu h1 h2 equal to 0 if you bring them all to the left hand side. Here, if these two guys are equal, you would be dividing by 0, so you can't conclude that the scalar product of h1 and h2 is equal to 0. So in this case, you're in a bit of a problem, because you can't really prove that h1 is orthogonal to h2. However, what you can prove, and we're not going to do that, is that you can take certain linear combinations of these two eigenfunctions. For example, a times h1 and b times h2, and then a different linear combination, c times h1 and d times h2. And you can prove that it's possible to choose these values a, b, c, d, to choose this linear combination in such a way that then these two new functions, which obviously will still then be solutions, that they will be orthogonal to each other. So in general, it will always be possible to construct eigenfunctions of a Hermitian operator which are orthogonal, even if you have degenerate modes. And by the way, this procedure of constructing orthogonal modes or orthogonal functions or orthogonal vectors out of degenerate individual modes or vectors, that's a certain procedure that has a name, and perhaps you've encountered this procedure in your linear algebra course to make things orthogonal, certain orthogonalization procedures. I see you going back deep in your memory. It's probably a couple of years ago. First name starts with another hint. Somebody remembers? I hear some whispering. No? Yeah? Yeah, that's the Gram-Schmidt orthogonalization procedure. So they're not really important for this course. I'm not going to ask you to construct such a linear combination, such a orthogonal. I just wanted to make a link with something you've seen earlier in your career and hopefully still remember. Okay, so that was about the orthogonality of the modes and about the concept of degenerate modes. Now, before I wrap up, I want to say something on what we mean by degenerate modes, and more specifically what we don't mean by degenerate modes. If we have a solution, so if we have theta h1 equal to omega mu1 h1, then of course we can write that theta alpha h1 is equal to omega mu1 alpha h2. So if we have a certain eigenfunction h1, then also alpha h1 is an eigenfunction. Same thing with eigenvectors in linear algebra. If you have an eigenvector, you can multiply it with any constant and you still have an eigenvector. However, here the terminology is that we don't say that h1 and alpha h1 They are degenerate modes. No, we consider them to be the same modes. They're not really degenerate, we call them the same, simply because it's so trivial, the relationship between the two of them. Another way of saying is that the eigenfunctions or eigenvectors from linear algebra, they're only defined up to proportionality constants. And we actually call H1 and alpha H1 the same modes, and not two different modes which have to be degenerate, simply because the relationship between their field profiles is so trivial. So we reserve the name degenerate modes for modes which really have a very different field profile, and by accident the same eigenvalue. Okay, that was all I wanted to say about Hermitian operators and their fun properties. After the break, we'll do something even more fun, namely going back to variational problems, which I'm sure you all like a lot. So we'll construct a variational approach to solving our eigenvalue problem. But that's for 15 minutes.